Um, okay, now let's get into the course and let's look at how we use computers in engineering. So I will just give a short introduction about the history of computers and computational approaches. Now, we are engineers and we want to design tools that can be used by the people. In fact, some of the tools that we want to design is not that simple and straightforward. Remember that we idealize the problems when we want to analyze, for example, a shaft or a beam or a column or a machine, as we have seen in strength of materials course and in statics. Generally, we need some more advanced tools in order to enhance our designs. And remember that we idealize the problems, so we reduce the problem to a one-dimensional problem in order to use the techniques that we learned in calculus. Okay, now let's consider a simple plate with a hole inside it. And of course, we want to predict the stress distribution. Now, it's very difficult to do it by using the techniques in strength, almost impossible. Certainly, we can use some theoretical approaches, which we are going to see in maybe in theory of elasticity. But still, it has some challenges. For example, the material here may not be homogeneous. It may be a composite material. It may have direction-dependent material properties and so forth. So how can we predict the stress distribution? Of course, we have different techniques, finite difference, finite volume, finite element. And what we do is very simple. We basically divide the whole area into sub-regions, and then we write the force equilibrium for each sub-region and try to predict the force transmission between different regions. Now, as we have seen here, since in the real case we have a circle, but when we divide the whole domain with triangles, now we have some edges and vertices. Okay, so what we do is we basically decrease the size of the triangles, and then we are getting closer to the almost circular shape. Certainly, this will increase the accuracy of our prediction. We will see what the accuracy is. Where do we use it? Of course, in many engineering problems, the structure that we are interested in is not that simple. So, for example, if you want to model surgery, we are talking about the human tissue, and it's highly complicated. You can try to simulate the working of a heart model. Okay, as you see, you want to predict the behavior of the muscles, heart muscles, or you can try to predict the response of hip replacement. What else? Of course, we design cars and vehicles, aircrafts, ships, and other things. Now, you design a suspension system and you want to predict its behavior. Instead of making an experiment, so you manufacture the spring and dashboard and everything, you put it on a car and you test it. it's better to simulate it in a computer, or you want to predict the loads acting on an aircraft, so pressure load. In fact, in this case, we have highly complicated geometry. Therefore, we use computers in order to predict the lift force and drag force and stability of the flow around the aircraft. What else? Certainly, we want to predict the pollution, air pollution in a city. So again, we use computers in order to predict the dispersion of a gas or a cloud, so whatever it is. In fact, we generally look at the problems from macroscopic point of view. So what is macroscopic? Just we know that every material or every structure is made of material. And in fact, material itself is formed by atoms. Somehow they come together and it has certain behavior. When you apply a load or when you heat it, when you give temperature, it certainly has a response. Of course, the inner structure of an object plays a critical role in the response of the object. In fact, we can use computers in order to predict the macroscopic behavior. So just think of a concrete column. So there are lots of voids and irregularities. Let's say we say that heterogeneities. And if we look at if we take a tiny piece and magnify it, and we see that again, it is almost identical. In fact, we use computers, and computers are doesn't care about they do not care about the inner structure. They mostly understand about the numbers. So what we do is we homogenize. We use homogenization techniques in order to model such kind of structures, and then we model it by using computers. This is, for example, if you think of a concrete column, we're talking about a 50-60 centimeters long column which has a width of 50-60 centimeters and a length of 3 meters. So we are talking about something very large. But of course, we may have different structures. So this is what we have around us. But on the other hand, just consider an electrode for electrocardiogram. Okay, you want to monitor, you want to measure the heartbeats of a human, then you use some sensors, some electrodes. Of course, in that case, you want to acquire lots of signals. Then what you use is simple nanoporous structure, possibly a nanoporous gold, and you model it in a computer. Of course, it's very difficult to measure it, and it is very difficult to test such kind of devices. So what we do is we model them in computers. As you see here, for example, here we see a skeleton of a nanoporous structure. You see the connectivity and everything. We can easily model them, and we can easily predict its response by using computers. What else? again, you may have some sensors. In fact, at a micron scale, then you want to predict the stress distribution because you want to know whether it will withstand to the applied load or not. And this is again where we use computers. Using computers allows us, computers and numerical methods allows us to predict their behavior and improve our designs. Of course, computational techniques and numerical methods are very recent. So we are talking about a 100 and 150 years old techniques at most. And from the beginning of the mechanical computers, we can say, or mechanical calculators, we mostly focus on number of floating operations. So what's a floating operation? Summation, subtraction, division, or multiplication. Now here we see a timeline, and the vertical axis is the number of floating operations. Here we see the computers, so beginning from the ENIAC, IBM 704, CDC 6000 and 6000. As we see in a logarithmic scale, it almost, the speed of the computers increases linearly in a logarithmic scale, or in other words, in real scale. So what's a logarithmic scale? So you just take the logarithm of it, the scale. For example, you see here 10 to the power 6 and then 10 to the power 4. So this distance is the logarithm of the difference, basically. And we see that in a logarithmic scale, the computer speed increases almost linearly. Now, in the first times of the computers, so like the ENIAC, here, for example, today in 2000s, they are using PCs, and PCs are, let's say, 1 million times faster than the first computer ENIAC, which was designed in 1950. What else? Of course, the cost of the computers and the computation decreases in time. So the CDC 6000 and 600 cost about $8 million in 1968. Now, in 2005, you see, we are talking about 1 megaflops, 1 million floating point operations, and now we are talking about 1 teraflops. So it's 10 to the power 12 almost. So cost about $500,000. So there is a decrease of approximately 16 times in the computer price, whereas the number of operations increased 1 million times. So for example, we are talking about 1,000 million floating point operations, and the cost for this is approximately $3,000. Of course, this is 2005. Now we are living in 2020, so it's much, much higher. So let's look at the salaries. So the salary in United States is $9,000 per year at that time. Now it is $50,000 around per year. Okay, so the university price doesn't apply to us at the moment. So for example, the price of a car, so the Mercedes cost about $7,000 in 1968, and now it is $900,000 to $100,000 at the moment. Therefore, we can easily say that the degrees of the computation is approximately 10 million to 100 million. So as the time passes, the computer speeds increases, the capacity of the computers increase. This decreases the computational cost. Of course, this decreases the cost of a design, because if you do not use computers, you have to make an experiment to validate your design. Let's look at the history of the computers, and let's look at the computers. So we know almost all of us knows about the abacus. So this can be considered as the first calculator. So each line of the abacus device is associated with the one digit. So if you have a 10 line, you have a 10-digit calculator. So in each line you have 10 buttons, and you play with it. We all know about it, I think. Then we have the Analytical Engine. So this is one of the first computers which was manufactured at the end of the 19th century. What else? So the Turing Machine was the first, can be considered as the first computers which is used for the encryption. Of course, it is again mechanical. It looks at the long strips of papers, and it just checks the holes. So basically the idea is whether there exists a hole or not. Then next is the ENIAC. This can be the first computer. Of course, you just plug different switches to different places. There are resistors and capacitive elements, and then you try to calculate the value. So, and in fact, what you see is the computer is as big as a room. So more than a room. In fact, it's as big as a building. Then the Univac is established. So it is 1950s, 1960s again. You see it is a little bit smaller. It has higher capacity, so it's much faster. Next is the IBM 701. You see it's getting smaller. In fact, still the computer doesn't have a screen. You don't see anything here, but at least the computer is as small as a room. Now here we see the first computer with a hard disk, or a disk drive, let's say. Not hard disk, but disk drive. Again, the ICs, the interconnected circuits, begin to be used in computers, then transistors, and IBM 5100 is the computer with the first screen. You have a tape driver in order to store data on it. It has a keyboard to write the code. So this is like 1970s. Now, when we come to the 1980s, of course, we faced with an Apple. As you see, it has an Hercules graphic card. In fact, you have two colors, keyboard. You have a floppy drive, which is 5.25 inch. Now, these floppy drives are capable of storing data of 320 kilobytes. We will see what the byte is. I know it's a little bit funny for you because the mobile phones in our pockets have a memory of 1 gigabyte. So approximately 1,000 or 10,000 times higher memory than the floppy drive. Now, in the 1980s, at the end of 1980s and at the beginning of the 1990s, Commodore 64 is the computer that is capable of giving us a sound card and a built-in sound card and a graphic card. Now we have 128 colors. This is a great improvement. Generally, the artists and the musicians were using these computers. It was expensive at that time. The data storage is done on tapes. Here you see a joystick. So the guy is playing a game with the computer you connected to your TV, and it has a memory of 64 kilobytes. Oh, well, this is my first computer. This is the first computer that I have used in my life, really. So this is an Amstrad PC. Actually, it is the one. It is 1520. So it has a memory of 520 kilobytes. I had the version of 1640, which has a memory of 640 kilobytes of RAM. Again, you see a floppy drive of 5.25 inch at the time. If you are rich enough, you can buy a hard drive with a 20 megabyte storage capacity at that time. So it has an Hercules graphic card. The one that I used has a Hercules graphic card which has only 2 colors on it. So this is the first computer that you use. Now possibly it has 4 gigabytes of RAM, maybe 500 gigabytes of hard drive, 1 million or 2 million colors, 3000 to 2000 pixel resolution. So we are talking about here, for example, 640 to 320 pixel resolution in black and white mode. So as you pass the color mode, of course, the resolution decreases. So this is simply the history of the computers. And as you see, the speed of the computers increases exponentially in time. Okay, so this is the history of the computers. So let's look at the numerical methods. Of course, our objective in this course is numerical approximations. We want to approximate the solution of some mathematical problems. If you look at the history, the first numerical approximation is used by the Egyptian. At that time, they were able to calculate the area of the circle, area of a triangle, and they want to predict the area of a circle. So what they do is very simple. In fact, they divide the circle into triangles, and they calculate the area of a triangle. Then they sum up the area of each triangle in order to approximate the area of the circle. As you increase the number of the triangles, of course, you are getting closer to the area of a triangle. This is the first, this is considered to be the first numerical method or numerical approximation in the human history. Then, of course, several improvements were done by Newton and many others. But after the invent of the calculus, so we are talking about the numbers from Avicenna or Ibn Sina, we know about then Fibonacci. People have been using numbers extensively, but then Isaac Newton began to denote the collection of numbers by using some variables. Then people begin to use functions in order to describe some of the physical things. So basically, we can consider a function as collection of points, an infinite number of points. This leads engineers to use analytical approaches, calculus mainly, in order to predict the behavior of a design. Therefore, before the computers, first step is the formulation. So you need a formulation. basically it is the fundamental laws explained briefly. So what is it? You need the law for the heat transfer, and then you solve it. You write the differential equation, possibly a partial differential, possibly an ordinary differential equation, and then you solve it. Or you have an integral equation. You solve an integral in order to predict the behavior. For example, we use an integral in order to calculate the resultant force of a distributed force, right? Then we use some approaches in order to solve this model problem. What else? Then we need an interpretation. Now, as the design gets complicated, you need more complicated functions, or you reach to a more complicated function. Now, this causes some difficulties. So, with the invent of the computers, again we use the same mathematical formulations, mathematical models. But now, use of computers allows us to model the problem with much more details. So we can get into the deep. For example, we can easily model the behavior of collection of atoms easily in computers. Then we use numerical techniques. Of course, this allows us, this gives us some advantages. We can easily visualize it on a screen, and we can easily have an idea about the problem. Therefore, we need a mathematical model first in order to solve a problem in computers. So, what is the origin of a mathematical problem? Of course, mathematical model. Of course, it comes from the theory. So you need a theory first. For example, you need the law for the heat transfer. You use Fourier heat transfer law if you want to solve a problem of heat conduction. Then you need data for it. What else? Heat conduction coefficient or the boundary conditions. So what will be, if you want to model the heat distribution in a ball, you need the temperature on either side, then heat conduction coefficient. So you need the data for it. Then what else? We need some tools to solve this model problem. So we want to approximate the derivative. We have a derivative in it. Like what? We can use finite difference, finite element, finite volume, or what else it is. At the end, after you get the solution, you can easily visualize it on a computer by using graphics. In fact, after we obtain the solution, we can make a judgment, and then we can improve the design. We can change the material easily just by changing the one parameter in our model instead of testing. Therefore, we can make lots of successive tests artificially. Then when we reach to a proper design, which is reasonable or which is feasible, let's say, then we implement it. So this is how we use computers and numerical techniques. Of course, when we are talking about a mathematical model, we have some definitions. For example, just think that you have a function. Now, this function mainly consists of independent variables. So what's an independent variable? It is a variable which doesn't depend on any other quantity. For example, position. For example, time. These are the independent variables. Sorry. We have parameters. So if you are solving a heat conduction problem, conduction coefficient is a parameter or Young modulus is a parameter. We have forcing functions. What are the forcing functions? For example, the temperatures. You in the either side of the ball, or flow rates at the end of a pipe, or pressure. These are the forcing functions because your model or your solution has to obey, has to comply with the values at the boundaries. At the end, you have a dependent variable. You have a solution, and what is dependent variable? For example, temperature is dependent variable because temperature depends on the position, time, and other things. So the temperature is a dependent variable. Or displacement is a dependent variable because displacement is a function of position as well. Or what else? Stress is a dependent variable because stress is a function of, again, position or time. Of course, you can solve different problems. For example, you may have a series of reactors for a process, for a chemical process. In this case, for example, you may have tanks which are connected, and you want to predict the flow rate of an object, and you use conservation of mass. And then you write a mass balance for it. Therefore, the difference between the material going out and coming in will give you the total amount of material inside a tank, for example. What else? You may have a truss structure. In this case, conservation of momentum or static equilibrium, force equilibrium has to be written for each node. This is what we have used. So remember that method of joints in statics. We write the force equilibrium for each joint, and then if we form a set of linear equations, and then we solve this set of linear equations in order to predict the force in each member. Of course, in order to do that, we need something between us and computers, because the computers are just complicated electronic circuits. And we write something on the screen, and this has to be converted to a language that can be understood by computers. Therefore, in order to do that, we use programming languages. So what are those programming languages? COBOL is one of those, very old. Maybe many of you doesn't know about it. Fortran, perhaps you have heard about it. We generally use it in engineering. BASIC is an old language. So Pascal is another one, old. C and Python. So probably many of you don't know about the COBOL, BASIC, and Pascal, but these are quite popular in 1980s and 1990s. And then Fortran is a very old, since 1970s. This is a formula translating language. In fact, this is called, but very recently Python and C comes into the play. So simply you write something on the screen, and then some command, and computer does it. But in real, it doesn't work like this. So there is something else, because we know that computer has a processor, some memory, okay, which we call RAM, random access memory. And of course, we have hard disks, which we store the information permanently, because RAM is erased. All the information in the RAM is gone when you close the computer. So anyway, what happens is like this. You have a programming language, you write your code, then you create an executable, some file from this series of commands. In fact, all the computers knows only one language, that is assembler. Assembler is the language of microprocessor, and assembler is microprocessor specific. So it is different for Intel processor, it is different for Motorola, and it is different for AMD processors. In fact, the software that they are using, the programming, converts the commands of the programming language into assembler, and assembler is sent to the microprocessor in order to perform the task. Be careful, here's another important thing. We recently have some mathematical packages. This mathematical packages simplifies our jobs greatly. They are specifically designed to perform some mathematical tasks, taking inverse of a matrix, taking derivatives, calculating integrals, solution of ordinary differential equations, or Fourier transform, or whatever it is. So they can perform many of the things that we have seen in calculus. So what are those mathematical packages? MATLAB is one of those, Matcat is one of those, Maple is another one, and Mathematica is the other one. Of course, there are some others, but these are the ones which are widely used and well known. In fact, Mathematica is quite good in symbolic calculations. Maple is also, but Mathematica is better. Matcat is good in if you are making some project work, if you constantly calculate the pretension force of a bolt, for example. MATLAB is good in arrays or matrices and vectors, vector operations generally. It is highly used in image processing and some other signal processing operations. But be careful, now all of these mathematical packages are mainly written by using these programming languages. So these are not, when you write something in these mathematical packages, this is not programming. Basically, this is scripting. You write a script. You write a MATLAB script, Matcat script, Maple script, or Mathematica script. So, for example, MATLAB is written in C because C is capable of doing operations even if you do not assign some values, some numbers to a variable. Therefore, so the engine of the MATLAB works with C. It's not possible, for example, for Fortran. Generally, this is why Fortran is preferred, especially in scientific computing, because you may easily make a mistake. What else? Now, when we look at the programming language, for example, here we see typical Fortran commands. Okay. So first of all, in order to write something in a programming language, you need to know about the type declarations. So what is a type declaration? There is a variable, and you have to define its type. Is it a real number? Is it an integer? Okay. So this is the command for real number, 4-byte real number, we will see what the byte is, and 8-byte real number, real 8. Then you define an integer. Will it be a string? So these are the type declarations. What else? You need to make, you need to define, you need to make an iteration. For example, you want to sum up the numbers from 1 to 10. This basically means that you make an iteration. You define a variable, for example, sum, then you add and you assign that its value is 0 initially, and then you add 1 to it. Then you proceed, in the next iteration you add 2. And you need an iteration variable, for example, here it is I. So I takes the value 1, 2, 3, 4, and goes like this up to n. And then it does the operations you write here n times in Fortran. This is iteration. What else? You need a conditional statement in order to write a code. So what's a conditional statement? For example, you want to write some the variables from 5 to 10 only. So you can either begin the iteration variable from 5, or you put a conditional statement inside the iteration, and you say that, okay, if I is greater than 5 or 4, and sum the value. This is what the conditional statement is. Of course, there are other conditional statements in and iterations comments in Fortran, but these are the things that we need to know at the beginning. Okay, let's look at the MATLAB. Now, in MATLAB, you don't need to make a type declaration, because if you say that a is equal to 5, a is equal to 5, it will automatically understand that a is a number. If you write at 5.0, a will be a real number. If you write a is equal to 5, it's an integer. This is what MATLAB understood, how MATLAB understood a variable. Of course, you can easily define the characters just putting into the quotation marks, and like this. So we will see in time. How about the conditional statement? You begin with an if comment. Again, if some variable, let's say a is greater than 5, do this, and you end the conditional statement. Here, for example, you end the iteration. So MATLAB has some similarities with Fortran, but of course there are several built-in functions, and this helps us in calculating some, in solving some engineering problems. Of course, when you write a program, in the first times of the computers, people generally use flow charting. So in flow charting, different symbols have different meanings. For example, you have a terminal here, you have flow lines, which shows you that in which direction you should go. So different symbols process input, output. So the decision, so basically this means this is used when there is a conditional statement, junction, off-page connector, and so forth. In fact, flow charting is not used anymore. Instead, people prefers pseudo-code. For example, here is a flow charting. For example, you write an algorithm, okay? So you write a code. There is a condition. This is a conditional statement. If, for example, a is bigger than 5, do this. Else, if a is smaller than 5, go to this command. So, for example, if a is bigger than 5, do this. Okay, go to the block 1, do the operation here, and then go to here. So do some comparison and check the value. If the value is this one, do this. If the value is something else, do another operation, and so on. Now let's look at the pseudo-code for the identical flow chart. Here we have an if condition 1, then do 1. If this condition 1 is not hold, check the condition 2, then do the block, do the operation 2. If this is not also done, check the operation 3 and 4 and so on. Here test expression. So an expression is checked. For example, if a is greater than 5. This is rather different than the conditional statement, but text expression. So basically, you choose one of these statements depending on the text expression here, and it is done. Okay. So again, here is a flow chart of an iteration. For example, let's look at it. You begin from here, do the block 1. Okay. Then go to the conditional statement. If conditional statement is true, so get out of the loop. Else, if conditional statement is not satisfied, do block 1 and then go back. So there is an iteration here, as you see. This is the Potato code of this flow chart. Now let's look at this Potato code. Again, you begin from a point. If I is bigger than some value, so stop. Else, begin from some value of I and go to the next operation. If it's false, do the block, go back, increase the I, and continue until it's finished. If I is bigger than certain value, then exit, get out of the loop. So this is a short introduction about the programming. Now, in the next course, we will continue about the error and accuracy, and we will begin to get into some introductory level MATLAB. Okay, thank you.